Right, welcome everyone to the 57th, I think this is 57, yeah. Welcome everyone to the 52nd meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Teresa Conde from the University of Stuttgart, and she will be talking to us about functorial approach to rank functions.
Thank you very much for the introduction and also for having invited me. The work I'll be talking about today is joined with Mikhail Gorsky, Frederik, and Alexandra Zvonareva. And as Frederik just mentioned, the theme is rank functions on triangulated categories, which is a class of functions that was quite recently introduced in a paper published last year by Chuang and Lazarev. Okay, so what's the plan for the talk? I have to wait a bit because my slides are not moving forward. Let's try again. Okay, good. So the plan is as follows. I'll start by telling you a bit about the predecessors of rank functions on triangulated categories, and then obviously I'll let you know what a rank function is, and I'll also mention some results in the work of Chuang and Lazarev that are going to be very relevant for the talk. And then in the second part, I'll try to explain how rank functions on triangulated categories are related to another class of functions which are called additive functions, and these are defined on abelian categories. So I'll explain how these two types of functions are related. And it turns out that these additive functions on abelian categories have been around for quite a long time, and they are very well studied, especially the integral ones. And so using the techniques that are going to be developed in part 2, we then are able to extract results on integral rank functions. And in the last part, we will focus on the case of compactly generated triangulated categories. So we will restrict to the case where our triangulated category is the category of compact objects and of some triangulated category, and we are going to derive some consequences in that situation. Okay, so let's start with the motivation/introduction. And it turns out that the idea of a rank function of Chuang and Lazarev comes from or draws its inspiration from functions which are actually defined for rings. So in order to see this relation, we are going to start by introducing these important functions on rings that are similar to rank functions. Okay, so for that, we are going to start by assuming that A is some unital ring, and for us, module is just going to mean a left module. And well, continuing with some standard notation, big mod A for us will be the category of all A modules, and small mod A is going to denote the subcategory of all finitely presented modules over A. Okay, so now we are all set to say what a character on the ring A is, or a character on small mod A is. And this is simply a function from the finitely presented A modules to the non-negative real numbers such that a couple of axioms are satisfied. So first, we want that our function is additive, i.e. it respects direct sums in a natural way. And we also want that our character row satisfies some sort of triangle inequality, meaning that whenever we have a right exact sequence like this one here of finitely presented A modules, we want that row of Y is smaller or equal to row of X plus row of Z, and moreover that row of Z is smaller or equal to row of Y. And if we moreover assume that row satisfies a normalization property, i.e. if we ask that row of our ring A is equal to 1, then we call this character row a Sylvester rank function. So a very easy example is if we consider A to be a field or a division ring, and if we take row just to be the dimension, then all these axioms are very easily verified. For another slightly more evolved example, let's consider phi to be some ring morphism from our underlying ring A to some other ring S, which we assume to be a simple Artinian ring. So in this case, by Artin-Wedderburn's theorem, we know that this S must be some matrix ring for some natural number n and some division ring D. And we can define a function on the finitely presented A modules through this quotient over here. And it's not very hard to check that this function row of phi is a Sylvester rank function on A, on small mod A, taking values on this abelian group. So to check additivity is quite easy, and it basically follows from the fact that the tensor product is distributed over direct sums, and the triangle inequality comes from essentially the fact that the tensor product is a right exact functor. And then if we plug in A, then we just get length of S divided by N, but as a module over itself, S is the sum of n isomorphic simple modules, we just get N over N, which is 1, and we have then checked all the axioms. Now, in fact, it turns out that a lot of Sylvester rank functions arise as in the example we have seen before. There's this beautiful result by Schofield. I think it's from 85, but maybe I should also be quoting here Cohn and Malcolmson. But well, the result says that the Sylvester rank functions on A taking values in 1 over n times z, where n ranges over the natural numbers, are in 1-to-1 correspondence with ring morphisms from A to S, where S is a simple Artinian ring. But actually, we identify some of these ring morphisms up to a certain equivalence relation. And the math is as expected. So if we pick some ring morphism, let's call it phi from A to some simple Artinian ring, we just assign to it the Sylvester rank function rho of phi, as we have seen before. Okay. So this talk is not about module Ket-reason, it's about, instead of triangulated Ket-reason, about an appropriate way to measure objects in triangulated Ket-reason. So a natural question is, what is the analog of a character or a Sylvester rank function, but in the world of triangulated Ket-reason? And the answer to that is exactly Chuang and Lazarev's notion of a rank function of triangulated Ket-reason. Okay, so let me just fix some notation. From now onwards, C is going to denote the skeletally small triangulated category, and we are going to denote the translation functor by sigma. So rank function on a category, on a triangulated category C, or better said, a rank function on the objects of the category C, is, as before, simply a function from of course, the objects of C to the non-negative real numbers, such that a couple of axioms are satisfied. As before, we want that rho is additive, so it preserves, in a way, direct sums of objects. And as before, we also want our function rho to satisfy some sort of triangle inequality, which in this case is translated into this inequality over here whenever we have a distinguished triangle of this type. And lastly, we are in a triangulated category, so we have translation functor. So the last thing one requires is that the function rho is sigma invariant. So if we translate our objects, then its rank doesn't change. Okay. Now there's another definition of a rank function, an alternative one, which deals with morphisms instead of objects. So it's now a function on morphisms of the triangulated category, and it is equivalent to the previous one. Let me just say how it looks like. So we say that a rank function on morphisms is just a function now, okay, from the morphisms of the triangulated category to the non-negative real numbers, and now additive on objects is simply replaced by the corresponding additive on morphisms. The triangle inequality condition is replaced by a rank nullity condition. So whenever we have a triangle like this one, we want that rho hat of the identity of Y is equal to rho hat of F plus rho hat of G. And lastly, the sigma invariance on objects is simply substituted by a sigma invariance on morphisms. And as I was hinting before, the two definitions that we have seen on objects and on morphisms are equivalent. This is a result, again, due to Chuang and Lazarev. And we can think a bit about this as the fact that on a vector space, the notion of dimension is essentially equivalent to the notion of rank of a linear map between vector spaces. We can define one from the other, and we can jump seamlessly between the two. And it's something of that kind that's happening in this case. So how does this bijection looks like? Well, if we start with a rank function on objects, let's call it rho, then one should assign to it the rank function rho hat, defined via this quotient over here. And in the other direction, if one starts with a rank function on morphisms, let's call it rho hat, then we define rho of x as rho hat of the identity of x. So this is how the bijection look like, and from now onwards we will jump between these two notions whenever it's convenient. Okay, so let's look at a couple of examples. Suppose now C is the category of perfect complexes over K, where K is a field or some division ring. Then in this case, all complexes are direct sums of translations of K. So it's quite clear that a row of K determines the whole rank function. So there's not much to be said in this case. And the same holds for any simple triangulated carry. And by a simple triangulated carry, I just mean triangulated carry with one, which is generated by one indecomposable object, and such that every triangle is a direct sum of split triangles. Okay, so for another example, let's now assume that C is the bounded derived carry of finite dimensional modules over a finite dimensional algebra A. And let's pick Y to be some perfect complex. So some complex which is quasi-isomorphic to a complex, a bounded complex of finite dimensional projectives. Then one can define a function, let's call it sigma of Y, on the objects of C in this way via the sum of these dimensions. And it's not hard to see that this gives a rank function on C. Note that since we have picked here Y to be a perfect complex, only finitely many of these dimensions are going to be non-zero. And as a particular case, we could take Y to be just A itself, seen as complex concentrated in degree 0. And in that case, what we get in this formula is just the dimension of the total cohomology. So that gives a rank function on C. Okay, so continuing with the examples, another source of ranked functions are the mass functions associated to Friesland stability conditions. This has been remarked and investigated in the paper by Chuang and Lazarev. And lastly, another example, which is more of a remark, whenever we have a triangulated functor from our base category C to some other triangulated category S, and we have moreover a rank function on S, then we can produce a rank function on C by pulling back a row along the functor phi. So we can define a rank function on C via this formula, and it's quite clear that this will satisfy the axioms. And this remarks such example should remind us about the example we have seen for Sylvester rank functions. Now, having in mind Schofield results describing all these Sylvester rank functions via morphisms from a ring to a simple Artinian ring, it makes sense to ask whether all rank functions, or which are the rank functions that come from a functor from C to S, where S is a simple triangulated category, through this pulling back procedure. And this question was partially answered by some results of Chuang and Lazarev. But before stating these results, I need to introduce some definitions. So we are going to say that a rank function rho on C is integral if its counterpart on morphisms only takes integral values.
I have a question. When you are phrasing this question in blue, the skeletally small assumption is still present, right? For both C and S?
Yeah. So, and all the unless I say otherwise, all the categories appearing are going to be skeletally small, because if they weren't, then note that our functions are functions whose domain are the objects of some category. And if the category is skeletally small, then and because the functions are actually invariant under isomorphism classes, this is all well defined, and that's why one needs all these smallness conditions. Yeah. Okay, so a rank function is integral if its version on morphisms only takes integral values. It is localizing if it is integral, and moreover, if whenever a morphism is such that its rank is 0, then the morphism should factor by some object whose rank is already 0. And lastly, we say that rank function is prime if it is integral, and if C has some thick generator such that rho of this thick generator, let's call it X, is 1. So this is a normalization property, and all these concepts were introduced in the paper by Chuang and Lazarev. Okay, so the theorem I was talking about before, I was hinting about before, is as follows. Let's assume that C, as before, is some skeletally small triangulated category. Moreover, let's assume it has some thick generator. Then there exists a bijection between prime localizing rank functions on C and thick subcategories, let's call K of C, such that C quotiented by K is a simple triangulated category. And going from 2 to 1, in order to go from 2 to 1, one should go by a pulling back procedure. So we have this Verdier quotient from C to a quotient of C. This quotient is a simple triangulated category, and there's a unique prime rank function there. And then if we pull back that rank function along the Verdier quotient functor, one gets the prime localizing rank function. And in the other way, we just take, in order to go from 1 to 2, one takes the kernel on objects of the rank function. In the particular case of a C being the category of perfect complexes of a cofibrilance DG algebra, then one can say more. In this case, 1 and 3 are also in bijection with equivalence classes of finite homological epimorphisms from A to S, where S is some simple Artinian DG algebra. I'm not going to say much about this right now, and some of these concepts I will leave them undefined, but we are going to revisit these results towards the end. Okay, so let's now move to the part where I tell you a bit about our results and about the methods we use in order to prove them. And for that, I'm going to continue with an analogy between two worlds as before. On one side, we have the abelian world, or slightly more general, a kernel compatible additive world. On the right-hand side, we have the triangulated world. So in this kernel compatible additive world, we can think of our category C as being, let's say, the category of finitely presented modules over some ring A, whereas in the triangulated world, we can think of C as any skeletally small triangulated category, for instance, the category of perfect complexes over some ring or over a DG algebra. Now, on the co-kernel compatible additive side, we have the notion of a character, and the counterpart on the triangulated world should be that of a rank function on C. And looking at characters, as far as I know, there are essentially two well-established ways to study them. So in the case, C is the carry of finitely presented modules over A, and if we require normalization property, then there's the work of Cohn, Malcolmson, and Schofield on Sylvester rank functions, and I've said a bit before about this already. Now, before, when we define the character, we have only defined them for rings, for carries of the type small mod A, but the definition makes sense more generally. And in this more general setting, and if one moreover restricts to characters taking integral values, there's a whole work by Crowley-Bovey and also by Ivo Herzog on this type of characters. And a nice thing about the work of Crowley-Bovey on this is the strategy. So the strategy is as follows. One starts with a character row on C, on our co-kernel compatible additive carry. And from C, one cooks up a better carry, which is actually a locally coherent carry. And then one can lift the function rho to another function, rho tilde, which is going to be an additive function. I'm going to say what that is in a moment. So that now we are in a better setting to study characters, because we are in a setting where our carries are better and our functions have maybe a slightly better property. And I've just written down below the formula for the locally coherent carry that should be cooked out of C, but this is just for curiosity. Okay. Now,
sorry, before you move on, can I ask, what's a co-kernel compatible additive category?
It should be a carry which is additive and it has co-kernels, something like that. Or one should can think of it as, so for instance, like the carry of finitely presented modules. Yeah.
Thanks.
Okay, so on the triangulated world, we have the rank functions, and if we restricted the case where C is a triangulated carry which has one thick generator, and if we require that the rank function satisfies some normalization property like the prime ones we have seen, then there are results of Chuang and Lazarev in this direction, like the ones that I've presented. But now we may conjecture whether something like the work of Crowley-Bovey and Herzog can be done for rank functions as well, namely to study the integral ones. Is there any type of strategy where from a triangulated carry we can associate maybe a locally coherent one and turn rank functions into these additive functions, which I have not defined yet, and study them in another setting and derive consequences about them. And so that's exactly what we are going to do. But first, I need to remind you some definitions. Okay, I recall that a Grothendieck category A is locally coherent if the subcategory of finitely presented objects is skeletally small and abelian, and if every object in our category is a direct limit of finitely presented objects. I didn't say what a finitely presented object is, but these are exactly the ones such that harming from them commutes with direct limits. Okay, and what is an additive function on a skeletally small abelian category? That is simply a function on the objects of the abelian category, taking non-negative real values, which is compatible with short exact sequences in the sense that the value of the function on the central object is equal to the sum of the values of the function on the outermost objects. Okay, now if you would try to follow Crowley-Bouvi's strategy and mimic this to study rank functions, maybe a first step would be to associate a locally coherent category to a triangulated category. But that's not very difficult, because if C is any skeletally small triangulated category, then the category mod C, i.e. the category of all contravariant additive functors from C to the category of abelian groups, is a locally coherent category. Moreover, not only is the category of finitely presented objects here abelian, that is just comes from the definition of locally coherent, it is actually Frobenius. I must say that from now onwards, we are going to denote the subcategory of finitely presented objects of big mod C simply by small mod C. And another nice thing is that every object in small mod C is represented by a morphism coming from the triangulated category. So every finitely presented functor is of the form im hom blank f from some more morphism f in the triangulated category. And a last fact that I must mention is that the translation functor on C gives rise to a translation functor on the module category of C, which is defined in this way. This is also an autoequivalence, of course. Okay, so our starting point to study rank functions is the following result. As usual, let's take C to be a skeletally small triangulated category. Then we have proved that rank functions on C are in one-to-one correspondence with sigma invariant additive functions on small mod C. I have not explained what a sigma invariant additive function is, but this is simply the sigma invariance property as before, but now the translation functor sigma here is replaced by its induction to big mod C, i.e. it's replaced by sigma star. And the way these two classes of functions are connected to each other is not very complicated. So if we pick a rank function, let's call it rho hat, a rank function on C, let's think of it as a rank function on the morphisms of C, then we can simply define rho tilde of f as rho hat of small f, where f is one of these morphisms representing the functor big F. as explained before. Okay, now as I was telling before, a lot of results are known about additive functions, especially in the case of integral additive functions. And now we have this translation result that allows us to go between rank functions and additive functions, and the goal is to transport and adapt results about additive functions on skeletally small abelian categories back to rank functions on our triangulated category. In the integral case, which is the case which is better studied. For that, let me give you some short summary of some well-known results about integral additive functions on skeletally small abelian categories. So for this quick part, let's suppose that be some skeletally small abelian category. Then we shall say that an additive function rho tilde on B is integral, well, if it takes integral values as expected, and we shall say that that is irreducible if it is integral, and moreover, if it is not possible to write this function as the sum of two other non-zero integral additive functions. So just the natural definition of irreducibility. Now, a very nice thing about integral additive functions is a result due to Crowley-Bouvier, which says that they decompose in a unique way as a sum of irreducible ones. So every integral additive function, rho tilde, decomposes as a possibly infinite sum of irreducible rank functions, but of course, when we plug in an object, only finitely many of these values are going to be non-zero, so this sum makes sense, even if it may have infinitely many summands. And because of these results of Crowley-Bouvier, it makes sense to talk about basic additive functions in the integral case. So we are going to say that an integral rank function is basic if there are no repetitions in the irreducible summands of its unique decomposition. Okay. There's another result that I want you to tell you about in this abelian locally coherent world. And for that, I need some more notions. First, we need the notion of an endofinite object. So now let's assume that A is locally coherent. So it's in particular, it's a big abelian category. We are going to say that an object X in A is endofinite if for every finitely presented object W, the length of hom Wx seen as a module over the endomorphism ring of X is finite. Okay, and another notion that we need is that the Ziegler spectrum of A, and the Ziegler spectrum of A is simply the set of all isoclasses of injective indecomposable objects in A. And this is not just a set, there's a topological structure in there where the opens are defined in this way as depicted in gray color. I don't have time to go through much detail about this, but yeah, this is a topological space where the opens are described in this way. Okay, so putting together results of Crowley-Bouvier, Herzog, Krause, and by doing some extra work that we could not find in the literature, one can prove the following bijection. So it turns out that the isoclasses of basic injective and the finite objects in our locally coherent category A are in one-to-one correspondence with basic additive functions on the finitely presented objects of A, which are in turn in bijective correspondence with Serre subcategories S of the category of finitely presented objects, such that the corresponding Serre quotient is an abelian length category. And by an abelian length category, I mean an abelian category where every object has a finite composition series. And lastly, all these topics are also in bijection with the closed discrete subsets of the Ziegler spectrum of A that satisfy the isolation property. So when I say closed, I mean closed for the topology I mentioned before. Discrete is they have the discrete subset topology, and the isolation property is a strange condition which says that for every object we pick in our closed set, well, this is an object in the category. If the singleton is an open in its closure, then we want that this quotient over here, this Serre quotient, has some simple object. Okay, this is what the isolation property says. And let me tell you a bit about how to go between these items. So in order to go, let's say, from 1 to 2, it's quite clear what to do, because I said that the end of finite objects are the ones that satisfy this property in terms of the length. So to an end of finite object in 1, we just assign to it into this length over itself, hom blank itself. And how is then 2 related to 3? Well, we are taking this Serre quotient, which we are saying that is an abelian length category. So in there, we have the notion of a composition length in this quotient, Fp of A modulo S. We can compute the composition length in here, and we pull back this composition length to the category Fp of A, and this gives rise to a basic additive function on Fp of A. And this is more or less how things are related. Okay, but we don't want to deal necessarily with skeletally small abelian categories. Our goal is to investigate rank functions on triangulated categories. So let's again assume, as before, that C is some skeletally small triangulated category. The notion of irreducibility that we have seen for additive functions also makes sense for integral rank functions, and we are going to say that a rank function is irreducible if it cannot be written as the sum of 2 non-zero integral irreducible rank functions. As an example, all the prime rank functions that we have seen before, these were these ones that satisfy this normalization property and were moreover integral. It's not hard to see that all of these are examples of irreducible rank functions. We have the following theorem, which is an analog of the result of Crowley-Duffy we have seen before. Using our translation result and adapting it, we can prove that every integral rank function on C decomposes in a unique way then as a sum of irreducible rank functions. Okay, so as before, it makes sense to talk about basic integral rank functions, i.e. the integral rank functions, such that there are no repetitions in their unique decomposition expression. And now, using the notion of a basic rank function, we can prove an analog of the bijection results we have seen before for additive functions. So first, we get a bijection between basic rank functions on C and basic sigma invariant additive functions on small mod C. This is simply our translation result, the one we have seen before, restricted to integral basic rank functions. But then adapting the theorem we have seen before, coming from results of Crowley-Povey, Herzog, and Krause, we also conclude that these are in one-to-one correspondence with basic endofinite homological functors H in big mod C that are invariant under this action of the translation. And in its turn, these are also in bijection with sigma invariant Serre subcategories as small mod C, such that the corresponding Serre quotient is an abelian length category. And hereby sigma invariant Serre subcategory, I just mean a Serre subcategory which is closed under the action of the induced translation functor sigma star that we have introduced before. And lastly, as expected, these items are also in bijection with the closed discrete, now sigma invariant subset of the Ziegler spectrum of B mod C that satisfy the isolation property as stated before. And now again, sigma invariant subsets means closed subsets, in this case, closed subsets of the Ziegler spectrum that are such that, well, if we apply sigma star to the whole set, we get back the same set again. Okay. Now, in the beginning, I said that towards the end, we were going to revisit the results of Chuang and Lazarev, and what we are going to try to do now is to state a more general version of it, but a version that still makes a connection between rank functions and localization theory of the triangulated category C, and not localization theory of the module category of C, as we have seen in the previous result. So in order to do that, our previous results were about these basic rank functions. These are integral rank functions. In order to now go to the localization theory of the triangulated category itself, we have to restrict to more specific types of rank functions. And for this, we need to define two new types of rank functions. The exact rank functions. So we are going to say that a rank function rho on C is exact if it is integral, and if this Serre quotient has an exact right adjoint. So here we are on this side, we are quotienting mod C by the kernel of the lift of rho to big mod C. So rho tilde is the corresponding additive function, and we are closing it under direct limits. Okay, and this is how exact rank functions are defined. We ask for such a function to have an exact right adjoint. And the second definition is that of an idempotent rank function. So we shall say that a rank function is idempotent if it is integral and if the kernel of morphisms of this rank function, i.e. the class of all morphisms which are mapped to 0 by the rank function, we want this to be an idempotent ideal. So we want that if the rank of a function is 0, if the rank of a morphism on C is 0, then this morphism should already be the composition of two other morphisms whose rank is already 0. Okay, so as an example, the localizing rank functions of Chuang and Lazarev that we have seen before, these are instances of both exact and idempotent rank functions. Okay, so I said that we needed to consider more particular types of rank functions in here, and we also need now to consider special types of functors from our triangulated category C. And for that, we need to define what an exact quotient functor and what a homological quotient functor is in the sense of Krause. So we shall say that a triangulated functor from our base triangulated category C to another triangulated category D is homological if whenever we have a homological functor, okay, from C to an abelian category, such that the class of morphisms which are annihilated by phi is contained in the class of morphisms annihilated by H. Well, whenever we have such a functor, then such a functor should factor through our original functor pi. That's what being a homological quotient means. The notion of an exact quotient is quite similar. So to define an exact quotient, we just replace here the word homological by a triangulated functor. And again, here, this should factor through using a triangulated functor. So that's the definition of an exact quotient. We just replace homological functor now by triangulated functor. And following Krause, a C quotient functor is simply a functor which is both homological and exact. Okay. And the typical example of C quotient functors are Vertier localizations. So it's good that Vertier localizations are contained in this class of triangulated functors. Okay. So now, using the notions we have defined and work of Krause, we are able to establish a bijection between the following two classes, between basic exact rank functions on C and equivalence classes of C quotient functors from C to a locally finite triangulated category. And by a locally finite triangulated category, I mean triangulated category, let's say D, such that the corresponding category small mod D is an abelian length category. Okay, and if in this theorem we restrict ourselves to localizing, to basic localizing rank functions, I said before that the localizing rank functions are exact, then we get a restricted bijection going from them, from the basic localizing rank functions, to thick subcategories of C, such that the corresponding Verdier quotient is locally finite. So you see that we get a generalization of the result by Chuang and Lazarev, where we no longer need to require that that the triangulated category has a thick generator, and we don't need the assumption of primality. Okay, and again, the idea as before of going between 1 and 2 is as follows. We have some functor from C to another triangulated category, which is locally finite, i.e. there's some composition length function looming in the background, and again we can pull it back to C. Essentially that's what's going on, and then we get our basic exact rank function. Okay, so just to conclude, we are now going to apply our results to the case where the category C is the category of compact objects of some compactly generated triangulated category. So throughout now, T is going to be a fixed compactly generated triangulated category, and C is going to be the subcategory of compact objects of T. Okay, so in this case, it's very nice that we can say how basic rank functions look like if C is the category of compact objects of T, then all basic rank functions are of this form. They are some length function where Z is some basic object in T, which is endofinite and which is invariant under the action of the translation. I didn't define what an endofinite object was in a triangulated category. I just said what it was in a locally coherent one. But basically, Z being endofinite means that this value here, this length over here, is finite whenever we plug in a compact object. Okay. Now, for the next result, we need to introduce the notion of a smashing subcategory, and a triangulated subcategory L of T is said to be smashing if it is closed under arbitrary coproducts, and if, moreover, the inclusion functor of L into T as a right adjoint which preserves coproducts. So that's what it means to be smashing. And before we have established a connection between rank functions and these C quotients investigated by Krause. And in the work of Krause, he actually establishes a connection between C quotients and smashing localization. So using work of Krause, we obtain as a corollary in the compactly generated case that that there is a bijection between exact rank functions and certain smashing subcategories. So in fact, the function mapping a rank function rho to this subcategory of T over here gives a bijection between basic idempotent rank functions on C and smashing subcategories L of T, such that the category of compact objects of the corresponding Verdier quotient is locally finite. A nice thing in this compactly generated case, which also follows from work of Krause, is that in this case, exact rank functions coincide with the idempotent ones, and this is why we are able to consider here idempotent rank functions. And lastly, the last thing I want to say is another consequence in the compactly generated case that ties our results to the third point in this bijection we have seen of Chuang and Lazarev, where DG algebras were involved. For this, I need to recall what a homological epimorphism of DG algebras is. So a morphism of DG algebras between DG algebras F from A to B is said to be an homological epimorphism if the corresponding restriction functor between the corresponding derived categories, i.e. the functor mapping a DG module over B to the same complex in here just by the restriction action, if this functor is fully faithful. So that's what it means to be homological epimorphism. And given two homological epimorphisms, we say that they are equivalent if the essential images of the corresponding restriction functors coincide. Now, using the work of Nicholas, one knows that homological epimorphisms parameterize smashing localization, smashing subcategories of the derived categories of DG algebras. So using this, we also obtain the following corollary. So in this case, let's assume that A is some cofibrant DG algebra. And we get then a bijection between basic idempotent rank functions on the category of on the perfect derived category of A, and also between equivalence classes of homological epimorphisms from A to B, where the category of perfect DGB modules is locally finite. So we also get an extension on the side of DG algebras of the result of Chuang and Lazarev. And yeah, I think this is all I wanted to say. Thank you very much.
Thank you, Teresa. Can we all unmute ourselves and give the speaker a round of applause? Okay, if you have any questions for the speaker, you can ask them now. Any questions? Well, I had a small comment. The section where you work with compactly generated triangulated categories, like we focus on the class of compacts. Is there any hope of doing that over well-generated triangulated categories?
Over?
Well-generated?
I don't know what that means. Okay. Can you tell me?
No, the definition is a bit complex. It's basically a generalization of compact generation. It's in
is this book. Like okay, like in this work of Janina and
the same thing.
Yeah, I don't know, okay. Possibly yes, but I have not thought about that. An idea could be to try to do some of these in tensor triangulated categories, but
stable infinity categories, like the list can go on. Any questions? Yeah, Peter.
Could I ask you a question? Hi, Teresa. That was very nice. I was wondering about some details. Like one thing is you have the hypothesis skeletally small in a lot of places, and I'm not really seeing why you need that hypothesis. Like if you had if you had isomorphic objects, wouldn't a rank function just extend to those other objects by defining it the same way on the other objects as the first one you thought of? And wouldn't it work to have it not scalarly small?
I mean, I don't know much about set theory and such things, but the thing is that if the category is not skeletally small, then the class of objects, the class of objects is a proper class. Even if it's skeletally small, the class of objects can be a proper class, not a set. But if it is skeletally small, the class of isoclasses of objects is a set. And so we can define, and because of the axioms of a rank function actually imply that the rank function on isomorphic things will have to be the same, then we should define them, instead of defining them on objects, we should define them on isoclasses of objects. But if the category is not skeletally small, this may be a proper class and not a set. And so it's a function that is not, whose domain is not a set. I think that's the problem.
Okay, I see. Yeah, I'm getting confused by all these definitions actually, and I see. So it's a set theoretic issue, really, that comes in. I was also wondering at one point, like I think when you at some stage when you defined a rank function, like in the sense of Chuang and Lazarev, you had like for a triangle, you have that row of y is less, an inequality is less than or equal to row of x plus row of z. And then later on, when you define a rank function on an abelian category, you have, I think, a short exact sequence, and row of y equals row of x plus row of z. And it might be, I might have tildes over the top at that stage. I mean, does this come out to be the same thing? I'm finding it confusing with the different contexts. Like, should I think of a rank function as one where where basically for the thing in the middle, the rank is the sum of the outer two terms, right? Or
sorry, what is the last thing?
Sure, because I think when you were defining it, oh yeah, so the original, the first definition that I've got has, and I think it's in mod A, if you have a right exact sequence, then row of z is less or equal to row of y is less or equal to row of x plus row of z.
Yeah.
And then later, when you were defining a rank function, I think you define it with a condition on exact sequences with an equality there, that the row
for additive functions on a skeletally small abelian category, with an equality, yes.
Yeah,
but
is there a difference?
This is okay. So this these are different things. These are different things, but they are related. As I was saying, the first thing with the inequality is a character, and characters can be defined on this. I was saying co-kernel, so additive categories with co-kernels. And then there's this construction of Crowley-Bouvier where we can cook up a new category out of this, which is, let's say, beta. And from the character, we can lift the character to this beta category, And on this better category, now it's going to be additive on short exact sequences. And yeah, this is a work of Crowley-Bouvier.
Okay, thank you. Thank you.
Thank you, Peter. Do we have any other questions for the speaker? Well, if that's not the case, let me thank you all for coming. This was the last talk of 2022. We'll be back in January. Okay, stop recording now.